So today we will discuss capacitors in series and parallel combination. Capacitors of various working voltages with certain standard capacities are used in electronic circuits. For a particular device, we need to change the value of capacitance according to the device need. To obtain the required value of capacitances, capacitors are placed in different combinations. Most simple ones are series and parallel connection. Now let's start our topic from the charging of single capacitor. This is an negative plate, positive plate, each and terminal of the battery. We discussed this before as well. The simplest way to charge a capacitor is to use a battery with proper wires, which is called a circuit. We know that charges can flow in a conductor when the circuit is completed. Electron will move through the wires by an electric field that the battery sets in. The field moves electron from capacitor plate H to the positive terminal of the battery, making H electron deficient, or the plate becomes positive charged. Similarly, the field derives the electrons from negative terminal of the battery to capacitor plate L, and plate L gains negative charge. Potential difference is 0 when the plates are uncharged. As the plates get charged, the potential difference increases until it becomes equal the potential difference between the terminal of the battery. Now, plate H and positive terminal of the battery is at the same potential. Similarly, negative plate L and negative terminal of the battery is at the same potential. The capacitor is said to be fully charged with a potential difference V and charge Q. So what will happen when the two capacitors are attached with a battery? There are two ways to arrange them in a circuit, either to place them parallel to each other and to place them in series combination. Further, the combination is replaced with equivalent capacitor, which means a single equivalent capacitor has the same capacitance as the actual combination of capacitors. This replacement of individual capacitors with equivalent capacitor simplify the circuit and makes the solution easier to find out unknown quantities in the circuit. Now let's start from the capacitors in series. Here two capacitors So here two capacitors are connected in series between the terminals of the battery, say at point A and B. Series mean the capacitors are wired serially after one after the other, and a potential difference V is applied across the two ends of the series. The potential difference that exists across the capacitor in the series produce identical charge Q on them, which we will discuss. So both capacitors are uncharged initially. When a constant potential difference is applied by battery, the capacitors becomes charged. How it works? Let's start from the top plate of capacitor C1, which acquire a positive charge. The electric field lines of the positive charge pulls the negative charge up to the bottom plate of C1 until all the field lines begin from the top plate and on the bottom plate. The negative charge on the bottom plate of capacitor 1 comes from the top plate of capacitor 2. Now the top plate of capacitor 2 becomes electron deficient and become positively charged. Now this positive charge pulls the negative charge from the connection at point B onto the bottom of plate of capacitor 2. So this becomes negative. Execute. The important point is the total charge on the lower part of C1 and the upper part of C2 together is 0 because these plates are not connected to anything except each other. So in series connection, the magnitude of the charge on all the plates remain same. Now let's look into three capacitors connected in series to a battery. Let's again revise the same exercise which we just did for two capacitors. This time let's start from capacitor 3 and work upward to capacitor 1. After turning on battery, okay, so after turning on battery, the bottom plate of C3 becomes negative. This negative plate repels negative charge on top plate of C3 and leave a positive charge on top plate of C3. So this becomes plus Q3. The repelled charge go to bottom plate of C2, capacitor 2, making it negatively charged. Again, the charge on the bottom plate of C2 repels negative charge from top plate of C2 to the bottom plate of C1. So this plate becomes positive charge and this one becomes negatively charged. Finally, the charge on the bottom plate of capacitor 1 helps to move negative charge from the top plate of capacitor 1 to the battery, leaving the top plate with positive charge. So here are two important points which need to be remembered about capacitors in series. First, when charge is shifted from one capacitor to another, in a series of capacitor, it can move along only one route, such as from capacitor 3 to capacitor 1. If there are additional routes, the capacitors are not in series. Second, the battery directly produces charges on only the two plates to which it is connected. Here, the bottom plate of C3 and the top plate of capacitor 1. Charges that are produced on the other plates are due merely to the shifting of charge already there. So the part of the circuit like this one is electrically isolated from the rest of the circuit, thus its charge can only be redistributed. It's the same thing which we discuss here. The net charge is 0 here. It's only a redistribution of charges. So let's do, okay, now we can draw a circuit for equivalent capacitor. Hence, the equivalent capacitor with equivalent capacitor has replaced the three actual capacitors. We can draw it like, so our circuit becomes and this is equivalent capacitor. With the terminals of the battery. Let's do some mathematics and derive an expression of equivalent capacitor of the series combination. We know Q is equal to CV. So let's find for every capacitor the value of potential difference. V1 becomes Q over C1, becomes Q over C2, 3 becomes Q over C3. So the total potential difference due to battery is the sum of V1 plus V2 plus V3, and it becomes Q 1 over C1 plus C2 plus 1 over C3. V over Q, we can also write V over Q is equal to C1 plus 1 over C2 plus 1 over C3. Equivalent capacitance is equal to Q over V becomes Q over Q to 1 over C1 plus 1 over C2 plus 1 over C3. Or we can write it as it is V over Q, so we can reverse it. We can also write it in this form. C it is 1 over C1 C3. We can easily extend it for n number of capacitors, the equivalent capacitance, so it becomes n capacitors in series. Now let's move to the other video to discuss the capacitors in parallel combination.